Hey, welcome back to Math with Patrick. Today is day 3, or January 3rd, of the Daily Epsilon calendar from the American Mathematical Society. And today, like January 1st, we have a geometry problem. Also, like the other two problems we've already done, the date, the 3rd, is the answer. So the area of this blue compound shape, these two triangles together, they are going to make 3 as their area. And it's up to us to figure out why that's the case. Looks like we're given some information here. I think this 2 times the square root of 2 times the fourth root of 3, this number is probably in reference to this side of this hexagon here. And well, what I'm noticing is it doesn't say that it's a regular hexagon. All it's telling me is that all the angles are congruent. I guess technically I could make a hexagon where all the angles are the same, but the sides aren't congruent. So here's like my example where all of these are, well, I'm approximating them, it's just a sketch, but all of these could be 60 degrees. And this is clearly not a regular hexagon because all of the sides are not congruent to each other. So it is possible to draw these kind of any which way, honestly. I could even make this top part even more narrow just to kind of prove my point that I could have any length I want. These are still 60 degrees. And so the fact that this bottom length is labeled doesn't necessarily translate to what the length is up here. But I don't think I could even solve this problem unless I assume that it's a regular hexagon. So we're going to go with that. So a regular polygon has congruent sides and congruent angles. And what that means for this problem is that we can assume that this length is the same as this one here. And at that point, the whole hexagon doesn't really matter for this problem. I'm just going to zoom in on this triangle here. So I'll draw the base. I'll label it with that 2 times root 2 times the fourth root of 3. Here's the rest of the triangle. And these tick marks here say that these two lengths are the same. As with these diagonals, the single tick marks say that these two sides are congruent in length. And lastly, I can assume that this is a vertical line and this is a horizontal one, so I should have some right angles here. Now it kind of looks like the 3 mini triangles in here are all the same in area. So these two, well, clearly are the same because of symmetry. But then it would be nice to say that this one is also the same as the other two. It kind of looks that way, and I believe I have a way to prove it. So the area formula for a triangle is half base times height. And the key thing here is that the base and the height need to be perpendicular to each other, or they make a right angle or a 90-degree angle with each other. So if I pick out specific lengths, I could prove that the area of those 3 mini triangles are all the same. So let's take a look at this one. I could say that the base is right here, and the height, again, it has to be perpendicular to the base, and so it's basically like this. I have to have, again, a perpendicular height, so this right here is my height, this right here is my base, and it looks like I could look a little bit down and see that this part right here is equivalent to the height of my triangle. And now if I take a look at this triangle right here, well, maybe I could call this part my base because it's the flat part. And then the height is perpendicular to the base. And both of these formulas use the exact same lengths because we were told that these were congruent. And then we can see that this length is the same as that one. So ultimately, these small triangles down here have the same area as these triangles up here. And let me clean up the diagram a little bit. So it turns out my initial assumption was wrong. Earlier I said that these 3 triangles are all equal in area, but actually it turns out that these 4 triangles are equal in area. And so if that's the case, then yes, I could prove the area or figure out the area of the top 2. I think it might be a little bit easier for myself if I actually just focus on the bottom 2. And just in the last segment, I proved that the area of the bottom 2 triangles is equal to the area of the top 2. So I'm going to solve for the area of the bottom two, but I know that the bottom two triangles have the same area as the top. So I will use my formula, half base times height. The base is pretty easy. I will just choose the entire bottom. So that will be that 2 times root 2 times the fourth root of 3. The half and this 2, when I multiply it out, those will cancel out. It'll just be a 1. So I can get rid of the half and that 2 from the base. And now all I need to worry about is figuring out this height. I made a few updates to the diagram. I color-coded the triangle and those areas that I was talking about, and then I decided to leave the 1/2 and the 2 separate, just so in the end I can show all my work. I also noticed something weird about the triangle, where it could actually be as tall as it wants to be. I could still follow the rules of those tick marks where these are equal in length, and these diagonals are equal in length, but the triangle itself could be really tall, and there's nothing really stopping me, except for the fact that these look like straight lines. So I'll have to go off that assumption that these are indeed straight lines, and therefore these angles here are both 60, and so that does make this an equilateral triangle on top. Then, if it's equilateral, I know that half of it is a 30, 60, 90 triangle. We saw this on January 1st. So there's the 90 in the corner, here's the 60 right here, and here is the 30. And once again, the relationship here is that if the short leg has a length of 1, I can multiply by root 3 to get the longer leg, or multiply by 2 to get the hypotenuse. So for this current example, the base is root 2 times the fourth root of 3. That is half of the whole bottom of the equilateral triangle. I'm essentially just knocking off this 2 to make it half as big. So going off that relationship between the legs, I could multiply by root 3 to get the longer leg. And so this is the length of the longer leg. And half of that is the height, because earlier we saw that these two lengths are equal. They both make up the whole height. So half of that is the height of that blue part, which I was solving for. So then I'll put half of root 2 times the fourth root of 3 times root 3. All of this together apparently is the number 3. So let's work through that multiplication and show that that's the case. Everything here is being multiplied. There's a half times a 2 times a root 2 times all the other things. And I know that I can do multiplication in any order. It's both commutative and associative. I can scramble it all up and it should still be the same. So let's start with the easy part. The half and that 2 cancel out. And the only other non-radical number I have is this half right here. So a half will come out. Then I think the next easiest part is to deal with these root 2's. Looks like I have a root 2 times a root 2. And that's essentially, just by definition, that's going to be 2. That's because the square root of something, when you multiply it by itself, it gets you that argument underneath. So root 2 times root 2 is going to be exactly 2. And I will put that here. Then let's deal with the hardest part first. Let's look at that root 3, or the fourth root of 3 times the fourth root of 3. Kind of going with that meaning of what is even a fourth root. This means that if I take the fourth root of 3 and multiply it by itself 4 times over, I will get 3. This is just by definition, this is what a fourth root means. Now I'll do something a little bit funky where I guess I could combine these together, and I'm not exactly sure what numbers those get, but it's something times itself, and that gives me 3. So I know that these together are going to make a square root of 3. And I guess I don't really need that index right there. If it's missing, you can just assume that it's a square root. So based on the meaning of what a fourth root is, it looks like if I multiply 2 of them together, I'll get the square root of 3. And that is how I'll combine those two together. Let's cross those off and create a square root of 3. And then finally, I have one more square root of 3 hanging out that I haven't dealt with. That's this one right here. This 1/2 and that 2, those cancel out and just give a 1. And then the square root of 3 times the square root of 3, that is just a 3. And I've proven that this blue area is a 3, and so therefore, since earlier I showed that both of these areas are the same, this region X is also a 3. And we're all done. Thanks again for tuning in to another episode, and I'll see you in the next one.